Hello everyone, welcome back to the channel. In today's video, we are going to learn one of the most important topics in embedded system, that is bare metal programming on STM32F401 CCU6. And especially we will configure analog input using ADC. But the best part is we are not using any HAL library, we are not using CubeMX generated code, or we are doing everything manually using the register programming. So if you truly want to master STM32 microcontrollers, understand the hardware deeply and crack the embedded interview, so this video is for you. So let's begin. So why bare metal? Many beginners directly start with HAL libraries. So that is the code provided by STMcube IDE or STMcube MX. So that is fine for the fast development. But if you don't understand registers, then you are only using the controller, not understanding it. Bare metal programming gives you full control of hardware, faster execution, small code size, better debugging skill, and strong embedded fundamentals. And most importantly, you will become a real firmware engineer. Our goal in this project is simple. We will use PA2 as an analog input, read the voltage using ADC, convert it to the digital value, use PA1 as LED. If analog value is high, then LED turn on. If analog value is lower than half of the value of ADC, then we are going to turn off the LED. So we will also understand every single register that we are going to configure. How we know which register to configure or where to write this value, right? So basically all these peripheral registers are memory mapped registers. So STM32 peripherals are connected through memory mapped registers. It means in the memory map, right, somewhere some memory is allocated for some registers, or particular memory is allocated for some registers, right? And writing some value to that register is either going to configure few of the bits, few of the value, right? Or reading from that memory is going to give us the ADC value, right? Or we are going to configure the GPIO pin as an ADC output, or simple digital input, digital output, right? So these are memory mapped registers. That means peripherals are controlled by writing values into the memory addresses. So let's take an example like GPIO A peripheral base address, like that we have seen into our previous videos. It is 40020000. Now, so from where this value is coming, right? If you go into the data sheet and if you search the memory map, then you will get all those things. Now, yes, so coming to this memory map, right, here you can see the boundary addresses, the peripheral, and the bus to which it is connected, right? So as I mentioned, GPIO A base address is 40020000, and it is connected to AHB1 bus. The RCC base address, again it is 40023800, and it is connected to AHB1 bus. So instead of function calls, we directly write the register value into these registers to configure those for our functionality or for our program. This is the core of the bare metal programming, that is to write the value directly into the registers. Now, so as I have mentioned earlier also, to enable any peripheral, we have to enable the peripheral clock of that particular peripheral. Now there are n number of peripherals like ADC, SPI, I2C, UART, DMA, right? Then there are timers, then there are interrupts, then there are watchdog. So there are multiple peripherals, and we have to enable the peripheral clock before writing the value into those peripheral registers. If you don't do this, then you cannot enable you cannot configure those registers. We have seen in our previous videos how to configure the GPIO pin as a digital input or digital output, right? We have written the code for that. We have seen where the ADC1 peripheral is, right? ADC1 peripheral clock enable bit is, it is in RCC APB2 ENR, and we have seen that it is on bit number 8, right? This we have seen from the data sheet. Okay, so I'm not going in detail for the data sheet. So we have seen that RCC2 APB2, that is the register in which we configure the ADC ADC1 peripheral clock enable. So here we'll configure APB2, right? This is reset. We want to check for the set. This is reset RCC APB2, right? This is peripheral clock enable registers. Now we have already seen this, that bit number 8 in RCC APB2 ENR register, it is for ADC1 peripheral clock enable. Okay, and writing 1, it disables the clock. So sorry, here it is wrongly mentioned. So writing 1, it enables the peripheral clock, and writing 0 to this bit number 8, it disables the peripheral clock of ADC1. Okay, so that we have seen, like we have to write bit number, or we have to set bit number 8 in the RCC APB2 ENR registers, that we have seen in our code also, right? So we were till this point, we have configured our code, or we have written our code till this point. Now we want to actually configure the ADC1 peripheral registers, so that we can use the ADC functionality, and we can configure one channel of ADC out of all these 16 channels. So we have seen till this point, like how to configure the APB2, or how to configure the ADC peripheral clock, right? How to enable the ADC1 peripheral clock. Now in the datasheet, if you go in the datasheet, right, and if you see the brief overview of the ADC, it is somewhere here, ADC, yes. So if you see the brief overview of the ADC, so in STM32F401 CCU6, we have one 12-bit analog to digital converter. Okay, and it has approx 16 channels, right? So if we calculate like how many bits there will be, what will be the maximum value, so it will come to 4095. That will be the digital value, right? If you map, like, because digital value, because like if you map it to 2 raised to 12, it becomes 4096. As we start the counting from 0, the final value becomes 4095. So FF will be 4095. Okay, not FF, but 0FFF. That will be the final value. Okay, now if you map it to 3.3 and calculate the data, you will get like what voltage will correspond to what value. Okay, so if 0 volt gives you 0, right, and 3.3 volt gives you 4095, then half of it, right, half of 4095, that comes to be 2048. So we'll get half of the voltage also, like 1.65 will be the voltage value. Now first thing, so this is for the ADC. This is very brief overview. If you want to see in detail, like you can go into the user manual, and in user manual you can hover to the analog to digital section, right? Now for this video, what we are going to use is, we are going to configure a single channel of ADC1 peripheral, right? We are going to configure the channel such that, like, we will start the trigger, not external but software start, we will read the value, and we will stop the ADC. So this will be the 3 simple steps. So first we will give a software start, then we will wait for the end of conversion, that is we will wait for ADC to complete its conversion, we will read the converted value, and we will stop the ADC. So these will be the 4 steps that we are going to configure. To configure the ADC peripheral, we need to check the required registers of ADC peripheral, right? So let's check the ADC peripheral or ADC registers related to ADC1 peripheral in the datasheet or the user manual. So in STM32F401 controller, ADC is 12-bit, as I mentioned. So 0 value corresponds to 0 volt, and 4095, this is the maximum value, 2 raised to 12, 409 becomes, so 2 raised to 12 becomes 4096 minus 1. This will be the final value, 4095. It is for full voltage. So full voltage will be 3.3, right? So if you take like half of this for 2048, it will correspond to 1.65 volts. So there are different modes of ADC. So ADC is powered by writing 1 to AD on bit. Okay. So this AD on bit, right? This AD on bit is in ADC CR2 register. Now I'm not telling by myself. I have learned this from the datasheet from the user manual. That's why I can confidently tell you that this bit, it is in ADC CR2, and I will also give you the bit position. Okay, don't worry about it. Now, as I mentioned, like we can have the start, like software start, we can have an external trigger, or we can have the injected channel start, right? So but for our tutorial or for this video, we are going to use a software start, right? We are going to tell ADC when to start and when to stop, right? When to stop will be the, like stop will be an command, okay, but when to start will be an command. We will wait for ADC. After that we will wait for an ADC to complete its conversion. We will read the value and then we will stop. Okay, now channel select. There are total 16 channels as we have seen in the datasheet. So we are going to use ADC channel 2. So we will need to select channel 2 for conversion. So there are, as we have seen in the datasheet, right, there are various modes. So continuous mode, then single shot, single conversion, continuous conversion, scan mode, right? Multiple channels configured. So there are various, but for our this tutorial we are going to use regular group single conversion. Okay. So regular groups, regular channels and orders in conversion sequence. So this must be selected, or this must be configured in ADC SQR registers. This is sequence register. So total number of conversions must be written into lower 320 bits of ADC1 SQR register. So for our tutorial we want only one conversion, that is on ADC channel 2, and then stop. Okay, so we want single conversion. ADC will start conversion, read the ADC value and stop it. Again in the while loop we'll again start, we'll read the value again and we will stop. So single conversion. Now we will start the single conversion using this software start bit, SW start bit, that is in ADC CR2 register. So read the value and again stop, right? So the value that we are going to read, it can be configured in two different modes. So there is right justified and there is left justified. See, any register of the STM controller, it is of 16 bit, correct? But our ADC value, it is of 12 bits. So either the left foremost bits can be 0 or right foremost bits can be 0. So most MSB nibble or most significant nibble, that can be 0, or left significant bit, right? LSB that we say, less significant nibble, that can be 0. So this is right justified, where the most significant nibble can be 0, not can be, must be 0. Okay, it is configured to be 0. So the ADC converted value will be written from bit 0 to bit number 11, and in in left justified, the ADC converted value will be stored from bit number 15 to bit number 4. Okay, so this will be the sequence, right? So turn on ADC, enable. So to turn on the ADC we have to write AD on bit. Okay, enable ADC by setting the AD on bit. Now ADC hardware power ons. To start the conversion manually, use SW start bit. Okay, that is in ADC CR2 registers. Now ADC samples the voltage on PA2 pin, then converts the analog signal into digital value. And step 3, it is like wait for the result, that is wait for end of conversion. We need to know when the conversion finishes. Okay, this is into the status register. We will see each register how it is and where it is. Okay, so ADCSR registers that I have, like these every notes I have taken, I have read the datasheet, user manual, and I am presenting it to you so that your efforts will be reduced. Okay, you can obviously go into the datasheet, verify this whether I am telling the truth or not, or this is simply just the thing. Okay, so these are the things. So select the resolution and select AD on bit, software start, align bit, configure bit, and everything. Okay, now we will come to the actual code part. See, we are configuring only channel 2, ADC channel 2. that we have to write into the sequence register. Okay, now we will come into the data sheet. Into the data sheet we will directly come to the register map, ADC register map. Okay, so we know that, okay, first thing, for single conversion, sample time and ADC, right? Yeah, so this is the exact sequence, right? In single conversion mode, ADC does only one conversion. This mode is started with count bit by setting 0. Okay, setting software start bit at ADC CR2 registers. So here you can see that software ADC will first power on the ADC, set the software start bit. Okay, then once the conversion is of the selected channel is complete, once the conversion of selected channel is complete, right, the end of conversion flag is set. So we check when the conversion is complete, that we are going to check continuously, and only after the conversion is complete we are going to read the value of the ADC. Else, if you read the value before the end of the conversion is completed, right, that flag is set, before that flag is set, if you read that value, ADC value, then obviously you are going to get an garbage value or an wrong value, and then you will wonder, oh, why we are getting the wrong value, correct? So you have to wait, you must wait for the end of conversion flag to be set. Okay, so we are coming over here, and then stops, ADC stops. Okay, this is single conversion. Now we will come to the ADC registers, directly come to the ADC register map. See, now SQR registers, sequence register, we are configuring channel 2, right, that we have to write. So regular channel sequence SQR bits, we will come to these bits, sequence bits, regular sequence bits, right? So if we come to like this, there are total 16 ADC channels that we have seen into the datasheet, right? So SQR1, SQR2 and SQR3. So if you observe this carefully, right, the first conversion has to be configured in ADC SQR3 register, and for that we are going to use 5 bits. Okay, for that we are going to use 5 bits. So this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. Okay, in SQR2 this is 7, this is 8, this is 9, this is 10, this is 11, this is 12, and in SQR1 this is 13, 14, 15, 16, and that's it. Okay, this is regular channel sequence length, how many conversions we want. So how many conversions we want, we have to write that value into ADC SQR1, this bit number 20 to 23. So for this tutorial we are going to use only single conversion, one conversion, that is on channel 2. So we have to write this 0000, or we can use the default value, reset value, that is 0000. Because we are going to use a single conversion, we are not going to write any sequence for 13, 14, 15 and 16. We will keep this value as reset values. Okay, so we are going to make sure that the SQR1 register, right, bit number 22, from bit number 20 to 23, we are setting it as 0 because we want only one conversion. Okay, and we'll configure ADC's regular sequence register 3, that is ADC SQR3, and we will configure these 5 bits from bit number 0 to bit number 4. Now we will see what value we want to configure into this register. So what you have to do is, there are total 16 registers, right, 16 channels rather. So we have to write channel 2, we want to write the channel 2, we have to write like the first sequence in the regular sequence, right, regular conversion, it is channel 2. So channel 2 means 1 0, so it will be 0 0 0 1 0. Okay, and the reset value is already 0 0 0 0, that is the reset value for this register is 0, and we want to configure these bits or we want to configure this field, SQ1 field, from bit number 4 to bit number 0, correct? And we want to configure channel 2, that is 2. Okay, so we can write, what we can do is we can OR with 0x02. So it will configure channel 2 for the first conversion in the sequence. So we have set the sequence, or we have configured the channel sequence. Okay, now what we want to do is we want to power on the ADC. Okay, we want to set the scan mode, right? We can set it to continuous scan, or we can set it to continuous conversion, sorry, single conversion. So we can control register 1 and control register 0, count bit, CONT bit, right? Continuous conversion bit. So see, ADC control register 1. So as we have seen, we can configure our ADC for the different resolution, like 12 bit, 10 bit, 8 bit and 6 bit, but we want only 12 bit. Okay, so in the resolution bits, RES bits, bit number from bit number 25 to 24 in ADC CR1, the value must be written as 00, but the reset value itself is 0x00, so we don't modify it, we will keep it as 0x00. Okay, and we will keep all those rest of the fields as 0x00. Scan mode, right? Scan mode is disabled. Yes, we want CONT bit. Now CONT bit lies in ADC CR2 registers. It is here. We'll see the significance of this bit, right? We'll see the significance of this register. CU continuous conversion. Setting it to 0, it is a single conversion, and setting it to 1, it is a continuous conversion. Okay, so it can be set by software and it can be cleared by the software. Set and cleared by the software. So what we will do is we'll set it for the continuous conversion. Now to set it to the continuous conversion, what value we have to write? We have to set bit number 1 to 1. So it will be 1 0, right? So it will be 1 and 0. So keeping rest of the registers, or keeping the reset value as it is, if you want to set it to 1, count bit or bit number 1 to 1, right? We have to write 2, because it will be 0 0 1 0. It makes the lower nibble as 2. So that's what we have done over here. We set bit number 1 to 1 by writing the value 0x00000002. Okay, now we have to power on the ADC, that is the bit number 0. Okay, so we have to set the last bit number 0 in the ADC CR2 registers. So for setting that bit, what we have done is we have OR the existing value with 0x01. So it will make the lower nibble as 0001, right? And it will set the AD on bit. Okay, so what AD on bit does, it powers the ADC module. Okay, now before coming to the configuration part, right, first thing we have to consider is to define the registers, right? So ADC1 base registers, we have taken this value from the datasheet in user manual. So its base value is 40010200. So that is the ADC1 peripheral base value, okay, base address rather. So after that, sequence register, we'll see all these offset. Sequence register, CR2, data register and status registers. We'll see all these offsets, right? But first we'll understand which registers we are configuring, which registers we are using, right? Now start the conversion. We start the conversion by setting the software start bit, right? That is bit number 30. So if you calculate the highest nibble, that is 0 1 0 0, that becomes 4. So we write 40000000. So we set bit number 30 to 1. I'll also in coming videos I'll explain how to write better code. This is very confusing actually. Like if you want to set particular bit, how we can easily set that without having a second thought, right? So that we'll see into the coming video, but for now just bear with me, right? And you will understand as we progress in the next videos, right, you will understand how we set the particular bit and what is the easiest method without any confusion. We will definitely see that method. Okay, but for now just bear with me till this point. Now we want to, like, we have done everything. We set the scan mode, right? We powered on the ADC. We set the like start of the conversion, that we have given like start the conversion of the regular channels, correct? Now we wait for end of conversion, and that wait bit, that end of conversion bit, it is in the status register. Okay, status register ADC SR register, that is bit number 1. Now we check in status registers, bit number 1 is like 20, because this is 0010. We check the value, we AND the value with 0x20. Okay, so we AND with bit number 1. So if the value is 0, it means that flag is not set, and we have earlier seen that until and unless the flag is set, means until and flag, when the flag set, right, after the conversion, ADC conversion is completed, after that the flag is set internally by the hardware, and we check on that flag, and until that flag is set, we do nothing, we just wait for that flag to be set. Okay, so we wait here for the EOC flag to be set. Once that flag is set, we read the value from the data register. Okay, now if the value is greater than half of the value, then we like power on the LED. If the value is greater than half of the value, then we reset that pin or we turn off the LED. So that is the code. Now we'll come over here in the register map. See, as I have mentioned that ADC1 peripheral, it is 000, right? It starts from 000 and it ends at 4C, right? But if you come into the RCC, if you come to the memory map, right, and if you come to the ADC1 peripheral, the base address, it is 40012000. So ADC1 peripheral base address we have defined over here, it is 40012000. That is ADC1 peripheral address. Now from the base address there are offset addresses, the peripheral registers, different peripheral registers, these are from the offset from the base address, right? So status register SR register, it is on the offset of 0x00. So status register ADC base address plus offset of 0x00. So that is SR register, status register. Now ADC CR1, that is control register, it is at the offset of 0x04. We have not used ADC CR1, that's why we can skip this. But ADC CR2, it is at offset of 0x08 from the base address. So ADC CR2, it is at offset of 0x08 from the base address. So base address plus offset of 0x08. Okay. Then comes the sequence registers. Sequence register offset of 2C from the base address. Sequence register 1, base address plus offset of 2C. Then sequence register 3, it is offset of 34. Sequence register 3, base address plus offset of 34. And data register, right, it is offset of 4C. The data register, it is offset of 4C from the base address. So this is the memory map for the ADC1 peripheral registers, right? So I hope you understand it thoroughly. If I have missed anything, right, I'll again go through the complete flow, right? We first enable the GPIO clock, then configure PA1 as an output. See, we first configure the GPIO clock, then we configure pin 1 as an output, then we configure pin 3 as an input. Okay, then we configure pin 2 as an analog input. So we have used the analog input functionality of PA2, right? Now we enable the ADC peripheral clock. Then we select channel 2. Then we we set the sequence. Then we set the conversion mode. Then we power on the ADC. Then we start the conversion using software start, right, by setting the SW start bit. Then we wait for the conversion to end, EOC flag to be set. Once the conversion is completed, we read the value. Once we read the value, we take certain action on the value depending on the ADC value, and then ADC automatically stops. Okay, we again come back over here, then read the value again. Right, now you can see a simple thing, right? We have set the continuous conversion mode. That's why we don't have to set this software start bit again and again. We just have to give it, or we just have to set it only once. Okay, if we have set it to single conversion and we want to read the ADC value again and again, then what we will have to do is we'll have to cut this code from over here and paste it into this while loop, forever while loop. Okay, so that will do the trick. So repeat forever is like that. Okay, so I'll again brief this whole video lecture into few parts or few things. So today we have learned how to configure ADC on STM32F401 CCU6 completely using the registers. There no HAL library were used, no CubeMX were used. We have used pure embedded code, embedded programming. So we have used pure embedded programming. So if you enjoyed this video, like, share and subscribe. In next video we'll see the actual output of this code. Okay, so without second thought, I will give you this output of this code onto the real hardware that I am using. Okay, so thanks for watching this video. We'll see you in the next video.